so kind of finish up this last example of linear regression. I'll then probably start kind of looking at the exam reviews, the practice exams. So we'll do that today and Friday. Next Monday, I previously was thinking about still doing a kind of a review day. I've got something that came up that I am not going to be able to kind of do those reviews, but I'll have all the videos from both sections, right? So I'll kind of work on different questions to make sure that every single question on those practice exams has a recording and is up by the end of the week, right? So between what we do here in class today and on Friday and what I do with my other sections, all of that will be up on YouTube page to kind of go look through any question you're having an issue with. Now, I have the answer keys up there, and one of them I kind of have like a detailed answer key. So those should be a pretty good resource, but just in case, you'll have those recordings. You can see me work through at least every single problem at least once. If you're going to have any issues with those, I'll also have Tuesday of next week. If you're kind of doing some last minute study, having any last minute questions, I'll be available the entire day, 9 to 5. So if you want to stop by my office, I might go out. I might run out to grab lunch or something. So if you do want to stop by, send me an email. I'll double check. I'll make sure that I'm not going to go away from the office end, but I'll be around the building the entire day. Okay? Also, if you're finishing up those homeworks, I've got office hours 2 to 4 today and tomorrow for kind of last minute questions on those. Other than that, it should set us up, I think, for everything. Any questions from you before we jump into stuff today? Okay. So those practice exams are going to be also mentioned pretty good, pretty accurate reflections of the kind of questions that I would ask you on the final. They're just not as long. So generally our exams have an hour, right? So we have now 20 questions in an hour. So if we got 2 hours for the final, 40 questions, but I'm going to cut that down to 30. So time should not be an issue at all going into that final. But the length of those practice exams will look a little bit different than the final, right? There will be 30 questions on the final. But all of those questions on the practice exams is very reflective of the types of questions I could ask you. And as we work through them, I'll kind of mention some additional kind of things here and there that might be good to know. Okay. Any questions? We're jumping into things here. All right. So we left off with this example where we had these kind of different racial combinations of officers and drivers. And we're looking at what's the impact that had on our Y variable, which last class we kind of had was just, did they get a ticket or not? So you can kind of think about it here. We'll just do, so it's multiplied by, right? We said the interpretation becomes a little bit different when our dependent variable is 1, 0, right? So now it's it's going to be the effect of a 1 unit change in our X variable, which our X variable is 0 to 1. So that's going from the 0 to the 1 group. Kind of our 0 base group that we left out was when the driver and officer were both white. So when the officer is white and the driver is non-white, relative to when the officer and driver are both white, here's the predicted change in our Y variable, right? So that's always the general form. That's the predicted change in our Y variable. If our Y variable is 1, 0, we said that's going to be a change in for the units there. We'll just have the last class. Anytime we have this 1, 0 variable, our coefficient is going to be the change in the probability, right? So it's the units are probabilities, right? Moving from that 0 to the 1 group for our dependent variable. So if we see kind of positive effects here on these kind of different race driver combinations, those are all relative to the group we left out. White driver, white officer. So if we find positive coefficients here, that's going to mean the probability you get a ticket relative to when the officer and driver are both white would be a little bit higher, right? And then sure enough, we kind of looked at the results and we found that they were all positive, right? So some evidence there's discrimination going on, and that's holding constant everything else in the decimal. We only include kind of driver's age and officer's years of service, but holding constant those factors. So the thought experiment is 2 traffic stops. The driver's the same age, officer has the same years of experience. But here, one of them, the officer and driver are both non-white, relative to when the officer and driver are both white. You predict that the probability they get a ticket goes up by about 0.18, or 18%. So it's a pretty sizable effect. Now we said we should be a little cautious with these results. Why? What's one statistic we look at to see kind of how accurate our predictions are? R squared. Yeah, R squared was really low, right? So R squared is essentially think about it as it's the amount of the Y variable that we can predict. Or to be more technical, the variation in that Y variable that all of our X variables explain, right? All of our kind of independent variables can explain. Well, here, the proportion that we're explaining is 0.03, so 3%. We're not explaining 97%, right? So there's still a lot of things that we've left out of this regression that probably matter, are very good predictors for whether or not you get a ticket. Right? Probably how fast you were going or where you were to keep, all these other things. So if we're not including some of these important variables, then our coefficients have what we call this bias component, right? As soon as we include those variables that matter on the right-hand side, we're eliminating the bias out of there. Right? So here, there's probably a lot of bias, right? Because there's 97% of things that we can't explain. Okay? We run the exact same regression, but instead we use this 1, 0 variable of whether or not the person was arrested at the traffic stop. Here, we get coefficients that are really, really close to 0. I mean, some of them are negative, which actually indicate that there's like reverse discrimination on that. Actually, when the officer is, non-white, the driver's white, they're actually a little bit less likely to kind of get arrested at that traffic stop. Now, we look at all of these estimates, right? They're very small, but also we look at our p-values. One of them is pretty close, right? It's not quite less than 0.1, but 0.127 is pretty close. But we can only reject the null if the p-value is less than alpha. We should always know our null, what we're assuming with these linear regressions, that there is no effect, so that slope is equal to 0. So here, if all of my p-values are not less than 0.1, I'm failing to reject this. Or really what I'm saying is I can't say that there's any effect between these race driver-officer race combinations and whether or not you get arrested, right? So I don't have very strong evidence that there's any kind of discrimination going on at the arrest level. However, when it comes to whether or not a ticket was issued, there we had p-values that, remember, e to the negative is 0, p-value is 0. Anytime you see this e to the negative in that p-value column, that means you can reject, right? Because your p-value is essentially 0 there. Okay. Any questions on this before we keep it over? Now, I wanted to point out here, take these results with a grain of salt as well. We get a really low R squared. Right? So it's not that we can't go through these regressions, interpret the coefficients, determine if they're significant, but even if we do that, we've got a really low R squared. We should be a little bit cautious of those results, right? Because there's still a lot that we can't explain here. What, 99.8% I can't explain. I'm explaining the proportion I'm explaining is 0.002, so about 2.2%. So probably means I need to go get more data if I really want to understand whether or not there's discrimination going on from officer-driver race combinations and whether or not someone gets a ticket or arrested. Okay. Questions on that before we keep moving? So I have kind of the results summarized here, but I think we'll go, well, we'll keep doing regression stuff, but I'll show you kind of just how we do this just in case you're kind of wrapping up that 50 stuff. So I think I mentioned last class that whenever we want to run a regression, we have to make sure that all of our X variables are next to each other. So we might have to do things like move some of our columns so that I'm getting all of these X variables I want to include on that right-hand side. Okay. Once I do that, reminder, you go to File, Options, Add-ins, Manager Add-ins. If you got a Mac, you just have to go to Tools and then down to Excel Add-ins, I think it says. Make sure we've got, oops, I didn't show you. Click the wrong thing. So add-ins, manage my add-ins. Make sure that analysis tool pack is selected. That gives me that data analysis option on the right-hand side there under my data tab. Right? Once you do it once, you shouldn't have to do it again. So we then go to data analysis. We'll go down here to regression, hit OK. So our Y variable, what we were trying to predict, that was whether or not someone was issued a ticket. So just Control-Shift, Command-Shift on a Mac, hit the down arrow.
We then go to select our X variables. Well, here I've got even more than what I showed you first. So I've got all these kind of different race kind of combinations. I also have kind of the driver's age, whether or not they're male, officer being male or not, officer's years of service, right? So Control Shift, Command Shift on Mac will select all of that, right? As long as I selected all of my variables here at the top, Control Shift should select all of them. And then make sure I said, okay, I selected my labels, hit OK, and I get my output here. All right, so I'll zoom in a little bit so we can see what we're doing. Okay, I get the R squared a little bit higher, not much, right? By including some of these additional control variables. But that's kind of how you would run your regression. Now you've got the output. You can start to interpret these different coefficients depending on what variable we're looking at. You could also make predictions. So this is one thing we said we could also do. So just to give another example of that, I'm going to delete these columns here just to get them out of our way. Remember I said, okay, really kind of all we're doing when we're doing these predictions is you have your original regression equation. So, it'd be something like age of the driver, all these other variables. Well, now that we have all those coefficient values, we could plug those in. Then we could come up with the hypothetical driver. So we would have the values, all those X variables. It's just one kind of long linear equation, right? So if you're thinking about the formula sheet you'll have, so if we come down here, basically what we're doing is using this guy right here to make our predictions for our Y variable. We've got all the coefficient values. Now it's just a matter of getting these hypothetical X values, okay? So, those would have to be given to us. So we said we'll always kind of include the intercept. So we're going to just multiply that by 1, right, to make sure it gets included. Here, let's say we've got let's say the driver's non-white, the officer is white. That means that both the driver and the officer being white would be a 0 as well, right? That's not the case. Let's say it's a 35-year-old male driver, the officer's female, right? So that would be a 0 for the officer kind of being male indicator. And then let's say, I don't know, they've got 12 years of service, right? So this is our hypothetical person, right? So sometimes when I give you this information, like I said, if I said, for instance, here, if the officer is female, well, that means that we put a 0 in for that variable, right? Because that variable is an indicator for just a 1 if the officer is male, 0 if not. We would then go through and we're just multiplying each coefficient for every variable by whatever the hypothetical value for that variable is, right? So take my coefficient, multiply it by this hypothetical value. Now, once again, I don't have to kind of multiply the intercept by 1 here. It's just an easy way to do it kind of quick. But I need to make sure that if I don't, I'm always including the intercept when I add everything up. This way, it'll have the intercept value in there for me. Right? So I copy this down, takes every single variable's coefficient, multiply by this person's hypothetical value for that X variable. And after that, it's just a matter of adding them all up, right? So you'll take every coefficient, multiply by that hypothetical X value, add them all up, and don't forget to add in the intercept. Right? So here we get kind of the predicted probability of this person when they got pulled over gets a ticket is about 0.41. Or 41% chance they get a ticket. Think of it that way. Okay. Any questions on this? If I was looking at these results, let's say at the 95% confidence level or 5% significance level, which of these variables can I not say has a significant relationship with whether or not you get a ticket? So think about which of these do not have a significant effect on getting a ticket. So if it doesn't have a significant effect, that would mean that I can't reject the null, right? Or I fail to reject. So if we're looking for which of these variables we can fail to reject the null at, our alpha is 0.05, we're really looking for what p-values are not less than 0.05, right? Every p-value that's less than 0.05, we're rejecting the null. We're saying that variable does have a significant relationship with our y variable, or does have a significant relationship with whether or not you get a ticket. Anytime we fail to reject that, we can't say that it has a significant relationship, right? We can't say that slope is different from 0. So we go through, look at these.
all these e to the negative, right? These are just p-value of 0. These are basically 0. The only variable that we can't reject the null at here, or we can't reject the null for, is what? The driver being male, right? We couldn't say that that had a significant impact on whether or not the driver gets a ticket at our 5% significance or 95% confidence level. Questions on that before we keep moving? Okay with that? So let's go to practice exam A. And we'll start here. We'll kind of keep doing some regression stuff. We'll kind of go back and do some older stuff, I think, focus more on Friday. But here I've got, probably have to give you some information. Here it is. So we've got a regression where our dependent variable is wage, right? So we're thinking about the variable we're trying to predict is somebody's wage. We're including all of these independent or X variables, right? Their years of education, their experience, their age, and then whether or not they're kind of male, right? So this variable is 1 if the individual is male, 0 if not. So I might give you some output that looks like this, right? So you've got all these different X variables included. You have what their coefficients are. I left out the test statistics because I'm trying to give you some really easy points with these, right? So remember, and actually I'll get this. No, I'll actually use this so that you kind of have my recorded work if you want to go back and look at it as you're studying for the exam. Maybe. All right, so what we're thinking about doing here is we've got our dependent variable of wage, right? That's our Y variable. We're going to have, I'll call this A plus B1 times, I think I had education times experience, age, and I think I just wrote it as gender, but just to make it a little bit easier, right? We kind of had this variable, which is a 1 if the individual is male, 0 if not. Okay? So I'm just writing out my regression equation. It's going to look something like this. Okay? I then ran that regression, and I got this output, right? So this is a little bit kind of small here. Let's zoom in a little bit. Okay. So I left out those test statistics, right? But before I even ask you to find a test statistic, we can start to interpret some of these variables, right? So how would I interpret that coefficient for education? Well, this example is a little easy because a lot of our variables have similar units, right? So general interpretation is always a 1 unit change in my X variable causes my predicted Y variable to change by whatever that coefficient is. So here, what's a 1 unit change in education? If we're measuring it, go back up here. How are we measuring education? Years of schooling. So what would my interpretation be for that coefficient?
That wage will increase by that much.
Yeah, so if my wage will increase by the coefficient associated with education, $1.23. I believe it's hourly wage, it says at the top. If I get 1 additional unit, right? A 1 unit change in that X variable. So 1 more year of schooling would predict that my hourly wage goes up by $1.23 based off of this data set, right? And I think this was mainly like lower paying jobs, a data set that I was running this off of. But you can think about why, right? So it doesn't matter what years of education you're looking at. If I plug a 10 in here, well, then 10 times that coefficient of 1.233 gets added in. If I go up by 1 unit, well, now how much additional, what additional value added in? Well, now instead of 10 times 1.23, it's 11 times 1.23. So there's an additional 1.23 there into my predicted Y value, right? That's why we can say it's always a 1 unit change in my X variable, right? If my X variable is up by 1 unit, so I get 1 more year of education, then the predicted Y value changes by whatever that coefficient is, in this case, $1.23. Questions on that?
How would I interpret my age variable? So what's a 1 unit change? Being 1 year older, right? I'm not trying to trick you with these, right? 1 unit is we're measuring age in years, so 1 additional year, you're older, right? You would predict that the hourly wage does what?
Basically, looks like it goes down.
Yeah, would actually decrease by 2 cents, right? $0.019 or 2 cents. Right? Now, why is that the case? I mean, the older you get, I don't know, maybe the less, whatever job this was, the less capable you were, or something like that. Now, it's kind of weird because if age goes up by 1 unit, most of the time, so is your experience, but it's, those kind of things go hand in hand. But here, that is how you would interpret that age variable, right? That holding everything else constant, so 2 people with the same age, same years of education, same years of experience, they're both either male or they're both female, but one of them is 1 year older, who would expect their wage to be a little bit less, right? 2 cents less, or $0.019 less. Questions on them? What if I wanted to know what's the effect of having 20 more years of experience? Yeah, so I look at that experience variable. I've got 0.417. All I do if I want the effect of something other than 1 unit is I just scale it up, right? Multiply it by how many unit increases I want. So if I want to know the effect of 20 additional years of experience, 0.41 times 20. Right? As simple as that. Right? Just kind of scaling it up, you're just multiplying that. Right? Any questions on that before we keep moving? So I could ask you to interpret any of those coefficients on the exam. Like if I gave you some output like this, I might ask you to interpret one of the slope coefficients. Now here, this isn't a question on this practice exam, but this is something that is fair game for me to ask when it comes to the final. How would I interpret the intercept? So I haven't hit on this one in a while, so we'll see if we can kind of remember. So how would I interpret the intercept here? So we said sometimes it's going to have a weird interpretation, but the way that we interpret this, I already forgot what it is. What is it? 8.68 about. So the way we interpret the intercept is this is the predicted value of our y variable if all of our x variables were equal to 0. So regardless of the example, that's always how we interpret the intercept. If all of our x variables are equal to 0, well, 0 times anything plus 0 times 8, right? These are all going to be zeros. The only thing we're left with is that intercept. So the intercept is going to be our predicted y value when all of our x variables are equal to 0, right? Might be a good thing to have kind of written down or jotted down, right? Our interpretation of our intercept, it's the predicted value of your y variable when all of your x variables are equal to 0. Okay. So that could be a question I ask you as well. Next one, another kind of fair game question, and this is where I'm trying to give you easy points. So I left off the test statistic here. If I wanted you to find the test statistic for this age variable, if I go to my formula sheet, it kind of has this reminder, this guy right here, which is how do I find my test statistic? I just take that coefficient estimate for the slope, divide it by the standard error. So here, I take the coefficient for the slope on that age variable, divide it by my standard error. So this is going to be what? Negative 0.019 divided by 0.083, right? And it's as simple as that, right? So I don't, hopefully this is not too tough. It's not like there's any easy mistakes you can make in your calculator. You just take that slope coefficient estimate, divide by the standard error, right? So we're going to get something close to 0.25 here, or negative, sorry. So if we look back, oops, maybe, there we go. I'm guessing we'll get negative 0.229, right? I rounded a little bit to think it was going to be on 0.25. Okay?
Any questions on that? That should be, like I said, I'm asking you for these test statistics from regression output. That should be like the easiest, one of the easiest questions on the exam. You just take the coefficient that's associated with that variable, divided by the standard error associated with that estimate. Okay. Questions on that? It's gonna be bad. I don't. Yeah, so I didn't have one in here, but here's another good question that you could be asked with some output like this. So, two questions. What percent of the variation can I explain of this hourly wage dependent Y variable? Yeah, so I go up to my R squared, right? Proportion that I'm explaining is about 0.368. So 36.8% of the variation I can explain in hourly wages, I can explain with education, experience, age, and gender. That still means there's what 60+% that I can't explain, right? But you know, pretty significantly higher than the other regressions we were looking at, right? To get kind of an R squared around 0.37 there. Which of these variables can I say has a significant relationship with hourly wage? And let's say we'll do at the 95% level again. So if I look at age, right, my p-value is 0.82. So am I going to be rejecting the null or not? It's 0.82. Right. We only reject if that p-value is less than alpha. What are we rejecting? We always start out assuming that those slopes are equal to 0. So my p-value is 0.82, and I'm using that kind of alpha of 0.05. It's not less than alpha, so I would fail to reject the null. If I'm failing to reject the null, I'm saying I can't actually say there's any relationship there, right? And I can't reject that that slope is equal to 0. So the only ones I can say have a significant relationship will be when I can reject the null, right? So if I look back here at that 95% confidence or 5% significance level, which of the variables can I say have a significant relationship with hourly wage? Yeah, I can reject the null for education, right? 0.002 less than 0.05. I can reject the null for experience. 0.005 is less than 0.05. I can't reject the null for the age or gender variable. So I can't say that age or gender has a significant effect or significant relationship with my Y, my hourly wage variable. I can say that education and experience do because I can reject the null there, or reject that slope is equal to 0, that there's no relationship. So when I'm looking for what variables have a significant relationship to our Y variable, it's going to be all of the variables for which I can reject the null. So every variable that has a p-value less than alpha, those are the variables I can say have a significant relationship. The ones that don't, I can't, right? Because I'm failing to reject that that slope is equal to 0. Questions on that idea or anything related to that? Okay. What if I had another question? So let's say, write something out as I talk. So let's say that I want to make a prediction for the hourly wage. Right? And I tell you, I want to make the prediction for this person who has 12 years of education, or so yeah, 12 years of education, 4 years of experience, they're 29 and they're female, right? So how would I go about doing that? So if I want to make a prediction for someone with 12 years of education, 4 years of experience, what did I say? They're 29 and they are female, right? How would I go about doing that? Yeah, so I would go through each one of these variables. I'll take the coefficient for that variable and multiply it by whatever that hypothetical value would be. So for the first one, right, 12 years of education. So 12 times 1.23 plus the next variable's coefficient times the hypothetical value for that variable. So plus 0.417 times 4 years of experience. Add to that the next coefficient. Well, here it's negative, so we'll have to be subtracting it, right? So minus 0.019 times 29 years old at the age, plus 2.29 with the female, and this gender variable is just a 1 if they're male, 0 if not. What would the x value be for that variable? So 0 times 2.9, it doesn't get added in, right? So all I was doing there, you could write out kind of how you predict your y variable, just plugging in those coefficients that we found. Then we have this hypothetical person. And it's just a matter of getting this entered into our calculator. And also one thing I didn't mention, we need to not forget, add in that intercept as well. Okay. So you go through every single variable, take its coefficient, multiply it by whatever this hypothetical person's value for x is, add them all up, and also include that intercept for that constant. Okay. Any questions on this idea? So this is like the real kind of important point of linear regression is that, yeah, we can run this regression. Yeah, it's great to interpret these coefficients and know the effect of any one variable changing on that y variable. We also want to make predictions, right? And once we have those coefficients, it's just a matter of plugging in this hypothetical person's values. Okay. All right. Let me think here. Come back to this in a second. Let me think if there's anything else I want to say on this regression output. So we talked about p-values, test statistics, predictions. That should kind of cover it, right? So if I'm outlining things to know how to do for linear regression, I can kind of give you the following. If you want to, I'm not going to write them down, but I will say them, right? So the first thing is you need to know how to find a test statistic, right? It's very easy. I already went through this. It's just the coefficient divided by the standard error. You need to be able to interpret slope coefficients. So this was the idea of a 1 unit change in that x variable causes the predicted y variable to change by whatever that slope coefficient is. You need to be able to interpret the intercept. We said that's the predicted value for y when all our x variables are equal to 0. You need to be able to use your p-values to determine whether or not you can reject the null. If you can reject the null, you're saying that variable has a significant relationship with the y variable. So knowing how to use those p-values to make our rejection decisions. What are you rejecting? You're rejecting that slope is equal to 0, or you're rejecting that there's no relationship. Said differently, you found evidence that there is a significant relationship. So part of kind of knowing that during that process, wink, wink, it might be a good thing to know that we always assume with linear regression that our null hypothesis is always that slope coefficient is equal to 0. What else do I want to say? Oh, and then the last thing we just did, sorry, no, 2 more things. But one of the last things is, you know how to make predictions for a hypothetical kind of person, right? And it might not be the concept of a person. It might be like, maybe I'm using some state level data. So make a prediction for this hypothetical state, right? Or whatever the observations are. So using those coefficients, being given some hypothetical x values, you need to know how to be able to make predictions. It's pretty easy, right? We're just kind of plugging these into kind of a long linear equation. And then the last thing, the final thing is know how to interpret the R-squared. Know what the R-squared tells you. And that was, it's the proportion of the variation in that y variable that you're explaining with all of your x variables. And then we kind of often convert that to a percentage by simply multiplying it by 100, right? If it's a proportion, make it a percentage, we would just multiply by 100. So those would be the things that you need to know kind of related to linear regression. Okay. Some other things that might be good to know just kind of related to those topics and just tie everything together. So let's say I had this regression and then I wanted to run another one. I'm going to include like, I don't know, what the person's, I don't know, what state they live in, maybe what sector they're working in, like all these other additional control variables. What's going to happen to my R-squared? It should go up, right? If I have more information, I should be able to explain more of the variation in hourly wages, right? Or make better predictions. Right? When you think of that R squared, as it gets closer to 1, we're just making more accurate predictions, right? Because we're capturing more of the things that matter. Let's stay here. I think that should be good. Any questions on any of the regression stuff? Otherwise, I might kind of go back a little bit and do some older stuff here. Okay.
So let me go all the way back here. To problem 1. So actually, we'll hit question 11 first, and then we'll go back to 1. So
other than the linear regression stuff, all we're going to have, so this final, I think I often do it comprehensive, but I've changed my mind. But I'm just going to do kind of what we've done since the last exam. So I think that'll make it a lot easier for you guys. You don't have to go all the way back to studying everything. It'll be just what we did since last exam. So we're going to hammer on that hypothesis testing stuff with 2 populations, right? We'll go through the types of examples we can see there, and then linear regression. So it's going to be about half and half, right? The first half, maybe a little bit, more like 16, 17 questions will be kind of that 2 population, like looking at the sample difference. And then the other half will kind of just be this kind of maybe a couple examples of linear regression output and me asking you to do all that various things I just listed off, okay? So that brings us to which of these types of examples do we use our standard normal distribution for, and which ones do we use a student t? So we have a couple types of examples, right? One, we were looking at the difference in sample means, and we were somehow given these known population variances, right? The other scenario we had was we were looking at the difference in our sample proportions, and these 2 scenarios, we were using the z-tables, right? Or these were the standard normal distributions. So if we were doing confidence intervals, or we're doing hypothesis testing, coming up with test statistics, looking at p-values, we were using that standard normal distribution. The other type of examples that we had the difference in my sample means when I only had sample variances. We then also had this example where we were looking at kind of creating this difference variable, and actually not hat, I think I have it D bar, my bad. And then kind of calculating that average of that new difference variable that we created, right? This was kind of called our matched pairs examples, right? So this is like we have the same population usually, but a before and after time period. The other kind of example that we had, and although we didn't go through, and I'm not going to make you like specifically look at the p-values that Excel is going to do that for us. Oh, sorry. Thank you. There we go. For our slope coefficients, right? Or our estimates for what those slopes are. Right? All of these were coming from that student t distributions or from those t tables. Okay. So I try to be pretty nice. I think even the practice exams, I probably wasn't as thorough. I will use this notation. So when I'm telling you on the exam, like, here's 2 groups, here's their sample mean, and here's their known population variance. Not only will I say that it, in words, it's the population variance, I'll also use the notation, which should make it a lot easier when you're going to the formula sheet to kind of identify, okay, yeah, here are examples where I'm looking for the difference in sample means, and I was given known population variances. Here's my confidence interval equation. Here's my test statistic equation. Difference in sample proportions. Here's my confidence interval equation. Here's my test statistic equation. Remember, we kind of had to break this one down into 2 steps. First, find this weighted average between the 2 proportions, and then calculate our test statistic. You won't have to use this equation, right? But this is how you would find the degrees of freedom. So kind of similar to the homeworks and then kind of everything you've done in class. I'll always give you what this assumed true degrees of freedom is if you have a situation where you're looking for the difference in sample means, but you only have sample variances. Notice it reminds you on the formula sheet, oh yeah, if that's the case, t-distribution, right? Confidence interval, test statistic equation. I think that's it here. Oh no, here's my matched pairs. Matched pairs, right, where we calculate this difference variable, confidence interval, test statistic. Our degrees of freedom here, I won't give you because it simply goes back to being n minus 1 for those matched pairs examples.
And then a lot of this you won't explicitly need. It's just kind of remember here is our y variable. Here's how we would predict y. Same kind of idea if we just have multiple variables on the right-hand side. I won't make you use these equations, right? This is kind of what Excel is doing behind the scenes for us, but just to kind of be complete here. Here's our test statistic equation for finding the test statistic for these different slope coefficients. And then kind of how we calculate that R squared, but really I'm not making you calculate that. I'm kind of just wanting you to be able to interpret. Okay. Any questions on that? All right, so this would be like I don't know, a good thing to have as you're kind of studying, kind of thinking about. We've really got 5 different types of examples. You're never using the t-tables when you look at these slope coefficients. Like we're always going to have those PIs in Excel. But matched pairs, or when you only have sample variances, t-tables. Proportions, or when you know the population variances, z-tables. Okay. All right, so let's go back to, and that's kind of what this was getting at, right? So here, if we're thinking about which one do we use the standard normal for, well, variances are unknown, matched pairs. Oh, proportions. Proportions are always the standard normal, right? So here, that answer would be D, right? That's the only one that we use the standard normal for. We'll scroll back up, and then we'll begin to work through one problem here, right? So this one, right, we've got 2 different sample means. And here, I actually did use notation. I thought maybe I didn't. But I only have sample variances, right? So what distribution am I going to have to be using here? All I have are sample variances. Right? All I have are sample variances. We're using that student t-table, right? The only time we use those z-tables if we have proportions or we know our population variances, right? Whoops, population variances right there. So we know we should be using the student t distribution here. In fact, I've got just these sample variances. If I go to my formula sheet, it even kind of reminds me, oh yeah, if I've only got sample variances, I need to be using that student t distribution. Okay. So if I want to find the confidence interval, right, and go to that formula sheet, it's really just a matter of plugging in the information we were given, and then we're going to have to find this t value, right? So I've got this formula in front of me. All I'm going to do is start plugging in the values that this problem gives me. So let me see here if I can remember all these. So write these down and we can kind of see what we're doing. So we've got what? First group sample mean is 27, sample variance of 25, and that was from 40 individuals. Second group sample mean is 29, variance 36, and we've got a sample size of 50. We want the 99% confidence interval. So what's our alpha going to be? 0.01, right? So 1% would be outside the interval. In decimal form, that's 0.01. Okay? So all I do is I have that formula sheet pulled up and I start plugging things in. So I'll write this out and then kind of keep going. So this was just the formula on the formula sheet. I'm going to plug everything in that I have. So 27 minus 29, plus or minus to get my upper and lower bound. 25 over 40 plus 36 over 50. Right? The only thing left I need to do is look up what that t-value is that gives me half of alpha in each tail. So we said two-tailed tests and confidence intervals are very similar, right? If we're looking up critical values for a two-tailed test, it's going to be the exact same process we use when we're looking up this p-value for confidence intervals, right? The number of standard deviations away we need to go to get alpha total in our tails, or half of alpha in each tail, right? Half of alpha here is going to be 0.005. So we want 0.005 in our tails, right? What's my degrees of freedom going to be? Well, this is one where, oh, I'm going to have to give you what that degrees of freedom is. So I go back and I give you, oh, an assumed true degrees of freedom of 50. right? Just assume that's what your degrees of freedom was if you use this nasty equation, right? So I've now got my degrees of freedom of 50. I want the area of 0.005. I go to my t-tables. Zoom in so we can see what we're doing. So I want 0.005 in the tail, go all the way down. Forgot to rotate the second page to a degrees of freedom of 50. So at degrees of freedom of 50, to get 0.005 in the tail, I need to go 2.678 standard deviations away. Now it's just a matter of getting this entered into our calculator. Now I'm never gonna try to trick you or give you multiple answers where the two of them have the same upper bound or same lower bound. So really you just need to calculate one of these, right? You either need to find the upper bound or find the lower bound. Once you do that, you'll be able to identify what the correct answer is, right? Now here, what value has to be smack dab in the middle of my confidence interval? Not 28, so be careful, right? What would this sample difference be? -2, right? So it should be centered around whatever that sample difference is, right? So -2 should be exactly in the middle of my confidence interval. Maybe I can rule some stuff out knowing that. I'm not sure on this one, but I can rule out D, right? -2 looks like it's kind of in the middle of the rest of these. Actually, I could rule out C technically as well. So -2 is not in this confidence interval, but why could I rule out C? Not only does -2 have to be in the interval, it has to be exactly in the middle, right? That's what I'm adding and subtracting in order there to. -2 is a lot closer to -1.2 than it is to -4.2. Might not be clear to see that right away, but you can look at that difference. It's out. It's not smack dab in the middle. From there, you just actually do that enter into a calculator, figure out if A or B is the right answer. They both look like they're centered around -2. Well, like I said, once you find the upper bound or the lower bound, you should then be able to identify what the correct answer is. You won't have to do both of them. Any questions on that before we keep going here? So, with these confidence intervals, once you have that formula sheet in front of you, the really only tricky part is kind of looking up that T value, right? It's going to be the value that gives you alpha over 2 on each side of the confidence interval. All right, so let's assume that we're going to do some type of hypothesis test, right? Here, I'm actually giving you the null and alternative. So one thing that I am still going to expect you to know how to do is to actually identify what the null and alternative hypothesis are. So for instance, this could be separated into kind of 2 different questions. So one would be, I ask you, okay, if you want to test for whether or not Indiana has a lower BMI than Ohio, what would the null and alternative hypothesis be, right? So if I said that I wanted to know, and I had this set up as Indiana minus Ohio, right? And I want to know, does Indiana have, I think it was lower BMI? Yeah, lower BMI. Then what am I wanting to know is true about this difference? Yeah, is it less than 0? That's what I want to test for. The way we generally write these are null and alternative hypothesis. We're just using the difference variable, right? So it helps sometimes to write out just to kind of think about, if Indiana was lower than Ohio, what would be true about that difference? But when we actually write the null and alternative hypothesis, we write it in terms of, is this difference less than 0? That's what we're trying to find. We assume the opposite is true, which is that it's greater than or equal to that. Another kind of key would be, what if I wanted to know, does Indiana have a different BMI value, I think it was, than Ohio? So if I see this term different than, what should I always be thinking about in my alternative hypothesis? Yeah, not equal to, and I'm always going to use these assumed true differences of 0, so that should also kind of help you identify these null alternative hypotheses. We assume the opposite is true, which is that exactly equal to 0. So this was a scenario that we actually had in the problem. So what type of tailed test would I have? Yeah, so the less than sign in my alternative hypothesis. So I've got a less than or a left tail test. Only evidence on the left-hand side is going to go against this null. Okay. From there, if you wanted to calculate the test statistic, once again, these test statistic ones are really just a matter of getting comfortable using your calculator to solve these problems. So if I go to my formula sheet, here's my test statistic equation. We've already discussed. I was given the sample means, given the sample variances, given the sample sizes. It's just a matter of getting this headed correctly in my calculator. Okay? Now, one thing that I always can kind of remember is my denominators are always representing standard deviations. So when it comes to these test statistics for the sample difference, it's really just about the sign of the test statistic will always be the same as the sign of whatever difference I found. Remember, we found earlier that sample difference was -2. So I automatically know that my test statistic has to be negative. From there, it's just a matter of getting this kind of entered in my calculator correctly. Okay? We'll go over that a little bit more on Friday. We'll kind of keep going through these practice exams, answer as many questions as possible. So if you have any questions that aren't from the practice exams or that are on it, make sure you bring those Friday and we'll kind of start with those. Okay. Oh, well,